So now we want to find the mass of a solid. So this will be a three-dimensional problem. It's bounded by z equals the square root of x squared plus y squared, which hopefully you know what that is off the top of your head. It's a cone, that's right, good. And z equals 4, which you definitely should know off the top of your head, that's a plane, right? If the delta function is equal to 7 grams per centimeters cubed. Now, just a side note here, just something to notice, that when your density is a uniform function like this, like 7, then your center of mass is called the centroid. It's kind of a special name for the center of mass when your density is uniform. Okay, so we have a cone and we have a plane, a horizontal plane cutting across it. So if we want to see that in Maple, I was having some issues getting this to graph beautifully, so I fussed around with using the plot functions. So I've got the plot of the cone right here, then I've got the region, and then the plane. And you can see them all graphed right here. So it's forming this lovely cone. And of course, how did I know about my limits of integration would be this? Well, I set the equation equal to each other. I set 4 equal to the square root of x squared plus y squared, and I solve it. So I've got my cone right here, and to find that region, I set the two z functions equal to each other, and I solved, and I know that's a circle of radius 4. So I know I could think of y as going from the negative square root of 16 minus x squared to the positive square root of 16 minus x squared. That's fine. So I've got that region down there. That's fine. So when I want to find the center of mass, or the centroid, I'm going to need the mass m first. So I'm going to need the triple integral of the density function over the course of that volume dv. Okay, well, let's see here. In xyz terms, I'd be letting, let's think, z go from the bottom of the cone to the top of the cone, so the bottom to the lid, if you will. And then I'd be letting y go from the negative square root, which is the bottom part of that semicircle, to the top of that semicircle, so negative square root of 16 minus x squared to positive square root of 16 minus x squared. And then x is going from negative 4 to 4. Now, that's kind of a pain. I mean, we can do it, but there's a lot of square roots roaming around in there, and that's kind of ugly. I'd have to involve a lot of square root substitution, and I don't even want to think about integrating the square root of x squared plus y squared with respect to y. Yuck. So, it would be a lot easier, especially with something like a cone, to do cylindrical coordinates. I mean, you could also do spherical coordinates if you so desired, but cylindrical would be nice and easy. So let's modify this. Let's change our limits of integration. So let's go back and look at this circle, and you might have noticed that I have this kind of radial spoke on there, and you might be thinking, why did I do that? Well, I'm doing it because I wanted to change my limits of integration. Not that this first integral we have wouldn't work, because it would, but if I have to do some stuff by hand, I don't want to do that one by hand. So let's think about this. I'm doing a full rotation, so theta is going to go from 0 to 2 pi. On a radial spoke, my radius is going from 0 to 4. Lovely. And then all I need to figure out is my z. Well, z is the square root of x squared plus y squared, so that would be the square root of r squared, which is r. So my z is going from r to 4. Simple as that, right? You start down here, r, and you work your way up to 4, and then r goes from 0 to 4, theta goes from 0 to 2 pi. Easy peasy, right? Those are actually a lot easier limits of integration than what I started with. Now my density function being constant helps because then it's just 7, so that's nice. And then I would change my limits of integration to 7, fine, and then r, remember we have to throw that in there when you do cylindrical coordinates. It's r dz dr d theta. So r gets thrown in there, so 7r, and then dz, where z is going from r to 4, dr, where r was going from 0 to 4, and d theta, 0 to 2 pi. And one of the reasons this is, well, there's so many reasons this is easier. I mean, first of all, look at those limits of integration. No ginormous square roots, none of that stuff. And another thing is that there's no theta in either the integrand or the limits of integration. So one of my first missions is going to be to get rid of that third integral entirely and basically do a double integral. A double integral, and then this integral is so simple. 7r with respect to z is just 7zr. So you put r and 4 in respectively. And that gives you, let's see here, 2 pi times 0 to 4, 28r, because 7 times 4 is 28, minus 7r squared, because you'd have r times r. And that's actually super easy, but I don't feel like doing it anyway. So I'm just going to make Maple do it. And let's see what I get. See, there's the original, just in case you don't believe me. This is rectangular coordinate system, just to show you that it works. And actually, I want to do something real quick. I want to actually press enter at the end of this here. So if I press enter, I want you to see how long this takes. I'm not going to pause the video. Do you see how long that took? Whereas if I go down to this one with r theta, and I press enter, it's like that. It's instantaneous. Right? It just proves what I was saying, which is that by hand, it's kind of annoying, right? But with the rectangular coordinate system, by hand it would just be forever. It means taking Maple a good long few seconds to do it. Whereas once I've changed it to cylindrical coordinates, it's very easy. Which, by the way, it would also be easy, relatively speaking, spherical, but with a cone, cylindrical will work great. Cylindrical will be beautiful, and in my opinion, easier than spherical. Spherical is great for spheres, right? It can work for cones too, but okay, so we've got that, and that's just to find m. Now keep in mind, we haven't finished this problem at all. All we did was find m. We haven't found the centers of mass. But let's think about this for a second. I'm finding the center of mass for a cone, but the cone is uniform density all the way through. So it has no heavy side or light side. It's just uniform all the way through. So the center of mass for x and y should be pretty obvious. It's on the z-axis, right? I mean, the center is going to be on this line that's going straight up through the cone. And it is. So that means that there's something for us to note, which is that the center of mass for x and y, the x bar and the y bar, are just going to be 0, because you're going to be on that z-axis, because the density function is uniform, delta is uniform, and the cone is symmetric. So because of both of those two factors existing, we're going to have x bar 0 and y bar 0. So that means all we have to find is z bar. Okay, z bar is mxy divided by m. So let me go back up real quick. Sorry. Yeah, so mxy divided by m, right? Where mxy is the moment in the xy plane, or about the xy plane. So what's the desire of this three-dimensional object to rotate around the xy plane? Okay, so I'm going to take the triple integral of z times delta of xyz and integrate it with respect to the volume of that solid D. I'm going to scroll back down. Okay, well, m is just a constant. We just found it. It's 448 pi over 3. So I'm just going to stick that in front. Oops, sorry about that. It does not like me. There we go. There we go. So z bar is mxy over m, which is 1 over m. See, just it's a constant, so I'm just putting it in front. And then my delta function was 7. And again, because it's a cone, cylindrical is just going to be way easier. I'm not even going to mess around with showing you the x, y, z. There's no point. Cylindrical will work fast and easy. So 1 over m is 1 over, what is this, 448 pi over 3. But of course, if I take 1 over a fraction, it's just going to cause it to flip over and become the reciprocal. So I have 3 over 448 pi. And then my limits of integration would go 0 to 2 pi for theta, 0 to 4 for r, and r to 4 for z. Same thing we found before. The difference is my integrand right here. So instead of just 7, like I had before, or 7r, excuse me. So I had 7r up here for the moment, or for the mass, excuse me, for the mass. I'm going to take 7rz, so 7zr dz dr d theta. When I integrate with that with respect to z, that would give me, here we go, 7rz squared over 2, right, because I add 1 to the power for z and divide by 2. And then what's going on out here is I had a 3 and there's no theta in this, so I just pulled 2 pi out. And 3 times 2 pi is 6 pi. Now you'll notice the pi's cancel, and 6 and 448 are both divisible by 2. So I reduced that fraction to 3 over 224 over here on the right. And then I'm sticking in 4 and r for z. So it becomes 7 times 4 squared, which is 7 times 16, which is yeah, 7 times 16, which is 56. Oh, 56, excuse me. It's 7 times 16 divided by 2, so it's 7 times 8, excuse me, which is 56. Sorry, I had to think about that. So 56r minus 7 halves r cubed, because there's nothing to cancel on that back one. Okay, so again, 7 times 16 is 112. 112 divided by 2 is 56. That's where that came from. And then I just made Maple do it. And it came up with an answer that kind of surprised me. So I was glad I checked myself. So I put in the original function and then I put in that reduced one that I had come up with. And both of them gave me 3. The answer is 3. Okay, so that means that my center of mass is 0, 0, 3, where each of those is in centimeters. And that's because my density was in, let me think, grams per centimeters cubed right here. So that means that the x, the y, and the z distances all have to be in centimeters. So x bar being the distance for the center of mass from the x-axis, which is 0, right? Y bar being the y-axis, 0, and then z, which is how high up it is going to be. So on that z-axis is going to be up 3 centimeters.